Today's lecture is a short video on the Hopital's rule, a technique for finding a limit value when it's in an indeterminate form. What kinds of indeterminate forms are we talking about here? Well, these two. The first one, 0 divided by 0. And the second one, infinity divided by infinity. And these two have to be inside a limit. Limit of 0 divided by 0 when x approaches a certain value. Let's call it a. Same thing here. Limit of infinity divided by infinity when x approaches a. As I mentioned earlier, this technique can only be used when the limit has the form of either 0 divided by 0 or infinity divided by infinity. As you know, these two are indeterminate. Forms. So you have to find other ways to find the limit value. Now, in the Hopital's rule, you can use this. Limit of f of x, the first function, divided by another function, g of x, when x approaches a certain value. Let's call it a. And the fraction between the two functions has to be in this form, 0 divided by 0, or infinity divided by infinity, either one of them. In this case, it's going to be equal to the limit of derivative of f with respect to x, f prime of x, divided by derivative of g with respect to x, g prime of x, at the same point when x approaches a. This is it, the only formula for the Hopital's rule. Once again, keep in mind that you can use this technique when you have 0 divided by 0 or infinity divided by infinity only. Now the question is, why does it work? Why all of a sudden a limit of f of x divided by g of x over here turns out to be equal to the limit of f prime of x divided by g prime of x in these circumstances? The actual proof of this turns out to be quite long and related to the Rolle's theorem. Which I think most of you are not familiar with. So here I'm going to take another route and give you an intuitive explanation instead. Before that, this explanation is borrowed from Mr. Derek Owens' channel on YouTube. So thanks to him, I found it to be great, easy to understand, and it can help us see why the Hopital's rule works. The link to the original explanation can be found in the description below. Now let's get started. Here we have two functions, f of x equal to x squared plus 3x minus 4, and another function, g of x equal to ln x. And then we want to find the limit of the fraction between them, f of x divided by g of x, when x approaches 1. Right here. So let's work on that down here. F of x, which is equal to x squared plus 3x minus 4 divided by g of x equal to ln x when x approaches 1. So the first approach I'm going to try here is the simplest one, direct sub. Put in x equal to 1 directly. I have 1 squared plus 3 times 1 minus 4 divided by ln of 1, and this is equal to 0. And down here I have another 0, ln of 1. As you can see here, we run into this indeterminate form, 0 divided by 0. So this one indeterminate. This means that we can't tell anything about this value, and we have to find another way to work on this. Before we continue, let's take a look at the graphs down here. I plotted f of x and g of x on a diagram, and this is what I got. The blue line, this is f of x, and the red line, this is ln of x, right here, g of x. So up here, we are interested in f of x and g of x when x approaches 1. the limit when x goes to 1, which means that we are interested at this point, right here at x equal to 1. And now I'm going to magnify the area around this point at x equal to 1, this area. And once I zoom in, this is what I got. The graph on the right hand side. Now let's take a look at the diagram on the right. What appear to be the curvy lines of f of x and g of x on the left hand side have now become the straight lines over here. This one is for fx, appears to be a straight line. This one down here, g of x. And this is true for any curve or any function out there. If you zoom in enough, it's going to appear to be a straight line. We call this process linearization. Make a note right here. Linearize by zooming in. Now these are the same lines as what we had on the left hand side. Once again, we are interested in this point at x equal to 1. Now let's add a few more things to this diagram. First of all, x-axis right here. We need this. And now the angle between the x-axis and the linearized f of x. Over here, this angle, let's call it theta. And now the angle between the x-axis and the linearized g of x. This angle, let's call it beta. At this point, I want you to focus on this location right here. Let's call it A1. Let's have this line as well, straight down. At A1, we have two function values. The first one up here, f at A1, and another function value down here, g at A1. Now let's move over to the left hand side. We want to find this tan theta. Tan theta equal to what? Let's find out. Well, tan theta is the ratio between the opposite side and the close side of the angle. So let's find them on the graph. The opposite side of theta should be this side right here. Over here, all the way down. And the length of this line, the height of it, f of A1. So we have the first term. The length of the opposite side, f of A1, divided by the close side, it's going to be this side down here on the x-axis, and the length of this one is going to be equal to A1 minus 1. So we have it over here, divided by A1 minus 1. But this is not enough for us. We need to find tan beta too. So tan beta down here equal to what? Once again, the ratio between the opposite side and the close side. The opposite side for beta should be this side right here. The length of this, of course, g of A1, the height of this line. So we have g of A1 over here. Now for the close side, it's going to be the same as the one we had before. The same line down here on the x-axis, all the way through. So for this one, it's going to be the same, divided by A1 minus 1. Now let's move a little bit closer to x equal to 1. At this point, a bit closer. Let's call this point A2. And let's have the same line, all the way down. At A2, we have two function values again. At this point, f of A2. And down here, g of A2. And now we want to find tan theta and tan beta at the new location, equal to what? Tan theta, the opposite side at this location, is going to be this. So this one, the length of this, the height of the line, is equal to f of A2. So over here we have f of A2 divided by this line and up to here. The length of this line is A2 minus 1. So let's put it over here. Divided by A2 minus 1. And now for tan beta. For the opposite side we have this one. This line. And the length of this, g of a2. So over here we have g of a2 divided by the closed side. Once again we have the same line down here on x-axis. And the length of this, a2 minus 1. Now let's move closer again to x equal to 1 one more time to this point right here. Let's call it a3. And we'll do everything all over again. Let's have this line. At a3 we have two function values. First one, f of a3. And another one down here, g of a3. Same thing over here, we find tan theta at the new point equal to the opposite side. This time it's going to be this side. The length of this, or the height of this, is equal to, once again, f of a3. So f of a3 over here divided by the closed side, this side down here. This time is a little bit shorter. The length of this is equal to a3 minus 1. Now for tan beta, the opposite side would be this side right here. This small line. The length of this is equal to g of a3 divided by the closed side again, and it's going to be the same black line. So this one, once again, the length of that is equal to a3 minus 1. Now I want you to imagine that this process keeps going until it gets very, very close to x equal to 1. So this is going to keep going this way until x approaches 1. Same thing over here. This fraction is going to keep going tan theta until x approaches 1. Same thing down here for tan beta. It keeps going until it's very, very close to 1, or x approaches 1. Now, the reason that we went through all of this trouble is because we want to find this fraction between tan theta and tan beta. So, division between tan theta and tan beta, divided right here. And it's going to be the same thing right here, division. Same thing here too. Over here and over here, until x gets really, really close to 1. Let's put the result of this division on the right-hand side. We have tan theta divided by tan beta. And it's equal to, now for the second term, let's take a look here. We can see that these two terms cancel. So what is left is this, f of a1 divided by g of a1. And now the next term. Once again, these two terms cancel. a2 minus 1 cancel with this. So we have this equal to f of a2 divided by g of a2. Now next term. And we have cancellation again. a3 minus 1 cancels with this one. So over here we have f of a3 divided by g of a3. And this is going to keep going until x gets really, really close to 1. Which means that we have this condition, limit, when x approaches 1. Now let's take a look at the numerators of this fraction. Over here we have the function value at a1, a little bit further away from x equal to 1, and over here we have another function value at a2, moving closer to x equal to 1. And once again, over here we have function value at a3, much closer to a1. And this keeps going, which means that the numerator is the function value of f. So we have f of x up here. And same down here, function value of g, further away, g again, closer and closer, which means that we have g of x down here for the denominator. So let's make a box around this. This limit right here is exactly the same as the limit that we wanted from the beginning. over here. Same thing. And it's equal to tan theta divided by tan beta. And it's also equal to the ratio between the blue line and the red line over here. F of A1 divided by G of A1. Same with the ratio over here, equal to the limit, and same over here. And obviously these ratios are not equal to 0. So make a note, ratios right here, not equal to 0 for sure. Which means that tan theta divided by tan beta must be non-zero. This term, non-zero and constant. As you can see here, the angles, theta doesn't change, and same thing with beta, it doesn't change. Which means that the limit that we wanted, f of x divided by g of x when x approaches 1, must be non-zero, not equal to 0. Because the ratio that we see over here, all of them are non-zero. And now we are going to observe these triangles down here in a slightly different way, in terms of the change in x value and the change in the function value. So let's make a note. Change in x and function of x as you move away from x equal to 1. At this point, I want you to imagine that you are standing right here at x equal to 1, over here. And then you are going to move away from this point to the right-hand side. In this direction, you are going to move away. Right here, take a step to the right-hand side. And let's assume that this step is so small. So this is delta x, a small step in x direction. Since we assume this step to be really small, I'm going to change delta x right here to dx. Differential x, a really small step in x direction. So let's make a box around this. Small step in x direction, it's dx. Now, after you take that small step, you are going to be at this point instead, at A3. At this point, we are going to observe the change in function value compared to the previous point. Before we took the step, we were right here at this point, x equal to 1. And the function value right here, f of 1, is equal to 0. At the new point, the function value has changed to f of A3. Which means that the change in the function value is going to go from here, f of 1 to f of A3. Which corresponds to this line, from down here and change it to over here. Once again, we assume that the triangle that we have here is so small, which means that the change in the function value we have here is also very small, which means that this is d of f of x. Now let's make a box around this. Really small change in the function value. At this point, I want you to check something. These two, f of A3 and d of fx, happen to be equal to one another here. Equal. The small change in the function value, d of fx, happens to be equal to the function value itself, f of x. So let's make a note right here. This is the key. In this situation, d of fx happens to be equal to the function value itself when it's near x equal to 1. When x approaches 1. Now let's make a box around this. You can also make a note down here that this happens when it's near root of the function f of x. The root is when the function value is equal to 0, right here. At this point, we have this condition, d of fx equal to f of x. Now let's move up here. We want to know the limit of f of x divided by g of x when x approaches 1. And right now we have this condition, 0 divided by 0. At this point, we also know that when x approaches 1, right here, it's near root of f of x and also g of x, which we can see it down here, near the root. This means that we can make use of the property we have right here. D of fx equal to f of x. So this is going to be equal to limit of x approaches 1. Now f of x is equal to d of fx at this point. D of fx divided by, now g of x equal to d of g of x. Small change in the function value of g. But I'm not going to stop right here. I'm going to divide both numerator and denominator with dx, differential x. Small step in x direction. And this term right here, df by dx, it's equal to f prime of x. And this one down here, dg of x divided by dx, this is g prime of x. Which means that over here we have limit when x approaches 1 of f prime of x divided by g prime of x. And that's why these two limits, this one and this one, are equal in this situation. And that is the main idea behind the L'Hopital's rule. So let's use it right away. At this point we have this condition, 0 divided by 0, which means that the limit that we wanted to find is going to be equal to f prime of x divided by g prime of x when x approaches 1. So we need to find f prime of x. F prime of x equal to, now we diff these terms. I diff them, I get 2x plus 3. What about g prime of x? G prime of x equal to, I diff this, ln x, I get 1 over x. 1 over x. So the limit up here is going to be equal to limit of f prime of x equal to 2x plus 3 divided by g prime of x, and by now we know it's equal to 1 over x when x approaches 1. And now I'm going to try the direct substitution again, putting in x equal to 1 into this expression. Over here, equal to 1, and same down here, equal to 1. And this is going to be equal to 2 times 1 plus 3 divided by 1 over 1. And this is equal to 5. The answer for this particular problem. Now let's move on to some examples in the next slide. In this example number 1, we need to find the limit of this fraction as x goes to 0. So the first approach I'm going to try here is the simplest one, direct substitution. D sub as the first step, which means that we are going to put in x equal to 0 into this expression. So what we have right here is square root of 0 plus 1 minus 0 divided by 2 minus 1 divided by, down here we have 0 square, and it's equal to, so over here we have 1 from the square root minus 0 minus 1 divided by 0, and here we have 0 divided by 0. So we have this form, 0 divided by 0, indeterminate, which also means that we can't tell anything about this. However, at this point, we know that when it comes to this form, 0 divided by 0, we can apply the L'Hopital's rule. So let's do that. Let's use L'Hopital's rule. Before we begin, let's assign the numerator to be f of x, the first function. And down here, x squared to be g of x, second function. Now we can apply the L'Hopital's rule down here. We know that we need to find this limit when x goes to 0, same point, of f prime of x. divided by g prime of x. And it's going to be equal to limit when x goes to 0. Now f prime of x, we need to find that. So let's diff these terms to find f prime of x. So let's make a note right here that square root of x plus 1, this is equal to x plus 1 to the power of 1 over 2. Let's start with this one right here, square root of x plus 1. Let's diff this. So the power comes down, 1 over 2. The inside stays the same, x plus 1, and now the power decreases by 1. So we have minus 1 over 2. And now we diff the inside the square root. We diff the inside right here, chain rule. The inside we get 1. So here we have 1 from chain rule. Now the next term, we diff minus x over 2. This one we get minus 1 over 2. Minus 1 over 2. And now we diff minus 1, a constant, it goes to 0. And now divided by, down here we diff x squared. We diff g of x to get g prime of x. So we have 2x down here. At this point, let's try direct sub again. After one round of L'Hopital's, let's try that, d sub. Which means that we put in x equal to 0. So 0 goes in here and here. So we have 1 over 2 times 0 plus 1 to the power of minus 1 over 2. Minus 1 over 2 divided by 2 times 0. These two terms are going to go to 1, which means that up here we have 1 over 2 minus 1 over 2. So 0 up here. Divided by, down here we have 2 times 0. It's equal to 0 again, down here. So once again we have this form, 0 divided by 0. After one round of L'Hopital's rule. It's still indeterminate and you can't tell anything about this. So our job is not done yet, so we have to do something about this. At this point, let's take a look here. This form is once again 0 divided by 0, which means that we can apply the L'Hopital's rule again. So make a note, can apply L'Hopital's again. So let's do that down here. L'Hopital the second time. Number 2. And this one is number 1. It's going to be equal to limit when x goes to 0. And now we have to diff one more time. We need to diff f prime of x again. And also this, diff g prime of x again. So we have over here f double prime of x divided by g double prime of x. Once again, keep in mind that you can do this when f prime of x divided by g prime of x equal to 0 divided by 0 in this form. So let's continue. Equal to limit when x goes to 0. And now we need to diff these terms. So let's start with this one. Let's diff this. The power is going to come down, so we have 1 over 2 times minus 1 over 2. So we have minus 1 over 4. The inside stays the same, x plus 1, and the power decreases by 1. So we have minus 3 over 2. And now we diff the inside, x plus 1. So we have another one down here. Now I diff this, minus 1 over 2, I get 0. So over here, nothing. Divided by, so I need to diff g prime of x again to get g double prime of x. So I need to diff this 2x, and I get 2 down here. And now after the second round of the L'Hopital's rule, I'm going to try direct sub again. So d sub, once again, x equal to 0. It's going to go in here alone. So these two terms are going to go to 1. So over here we have minus 1 over 4 times 1 divided by 2. and this is equal to minus 1 over 8. This value, minus 1 over 8, is the limit of f double prime divided by g double prime when x goes to 0 over here. And it's also equal to the limit of f prime divided by g prime when x goes to 0. And it's also equal to the limit of f of x divided by g of x, the limit that we wanted to find in the first place. So this is equal to minus 1 over 8. So this is our answer for this example. Before we move on to the second example, let's take a look at this part right here. And now let's have this limit of f of x divided by g of x. When x approaches a certain value, let's call it a. Let's assume that the function value at a, f of a, equal to 0. And same thing down here. G of a equal to 0. Which means that in this case we have limit x goes to a of 0 divided by 0, which is indeterminate. And we can also apply the L'Hopital's rule on. Make a note right here. Can apply L'Hopital's. At this point, I want you to do something. Let's arrange f of x and g of x inside this limit. Let's do it down here. It's the same limit again. X goes to a. But this time, I'm going to move f of x down to the denominator. So I flip it down here, and I have 1 over f of x. And then I move g of x to the numerator, which means that I flip it again, and it becomes 1 over g of x. Since the function value of f at a is equal to 0 up here, it means that down here we have 1 divided by 0. So this is going to go to infinity. And same thing with g. The function value of g at a is equal to 0, which means that over here we have 1 divided by 0. It's going to go to infinity as well. Which means that at this point down here we have limit when x goes to a of infinity divided by infinity. So let's have it right here. Infinity divided by infinity. Another type of indeterminate form. But as you can see here, these two limits are actually equal to one another. Equal. They just look different because of the rearrangement. This means that they are technically the same, which also means that if you can apply the L'Hopital's rule for this one, you can also apply it to this one down here. So make a note, can also apply L'Hopital's. And that's why the L'Hopital's works on both 0 divided by 0 and infinity divided by infinity, these two indeterminate forms. Because you can arrange 0 divided by 0 to be infinity divided by infinity and the other way around. Now let's work on example number 2. We are supposed to find the limit of this fraction. When x goes to infinity, this one is a little bit different. As usual, the first approach is direct sub, d sub, which means that we are going to put x equal to infinity into this expression. So it's going to be infinity plus 2 times infinity square divided by 3 times infinity square plus 5 times infinity equal to. So we have a really large number right here, plus a really large number again right here, even bigger. So up here we have infinity divided by, and down here we have a really large number square plus another large number of course, is going to go to infinity down here. And now we have this indeterminate form, infinity divided by infinity. But as we can see from the right hand side, we can apply the L'Hopital's rule here. So let's do that down here. L'Hopital. Once again, before we begin, we assign the numerator to be f of x and the denominator down here to be g of x. And now for the L'Hopital's rule, we have limit. When x goes to infinity, f prime of x divided by g prime of x equal to limit when x goes to infinity, just the same. And now we have to find this, f prime of x. So let's diff these terms right here. Let's start with the first one. Let's diff x, I get 1. Now I diff 2x squared, I get 4x plus 4x divided by, now g prime, we need this. So we need to diff these terms down here. Diff this, I get 6x. Next term, I diff this, I get 5. After the L'Hopital's rule, I'm going to apply the direct sub again. So over here, d sub. Once again, x equal to infinity. So we have 1 plus 4 times infinity divided by 6 times infinity plus 5. As you can see here, this is going to go to infinity. Same down here, infinity, which means that we still have this form. Infinity divided by infinity. And at this point, it means that it's still indeterminate. So we have to work on it more. As you can see here, we have infinity divided by infinity again, which means that we can apply the L'Hopital's rule again. So the second time, L'Hopital. Number 2 again. And this one is number 1. Just like what we did in example number 1, we need to diff f prime right here. And also g prime. Limit. When x goes to infinity, you diff f prime, you get f double prime. F double prime of x divided by, you diff g prime, you get g double prime. G double prime of x equal to, now we keep the limit. X goes to infinity. Now we need to diff these terms. 1 plus 4x. Diff 1, it goes to 0, so nothing at the front. Now we diff 4x, we get 4. Divided by, now we need to diff these terms. 6x plus 5. You diff 6x, you get 6. You diff 5, it goes to 0. Now let's cancel these two. This becomes 2 and this becomes 3. Which means that this limit is equal to 2 over 3. And this value is the limit of f double prime divided by g double prime. And it's also equal to the limit of f prime divided by g prime. And it's also the limit of f of x divided by g of x when x goes to infinity. And this is the answer for this example, 2 over 3.